Good morning. Thanks for coming this morning. I'm here to talk about TypeScript's type system. I came to TypeScript in kind of a roundabout way. I'd been looking for a language I could use to do statically typed functional programming and I'd been looking at F# and ReasonML, and I found myself kind of surprised to land on TypeScript. I work at a consultancy called Atomic Object, and we do a lot of different kinds of work. We're a product development consultancy. We do mobile, desktop, web, API work. And I wanted a language that would work across the broad spectrum of projects that we do, both on the technical side but also on the non-technical side. In particular, I wanted something that would be comfortable for a lot of different clients and a lot of different stakeholders. So TypeScript, it's kind of a lot of different things. First and foremost, it's a language. It's a strict superset of JavaScript. It adds a type system to JavaScript, giving it its name. It's also very configurable. You can target many different use cases and in different strictness levels. We use TypeScript at the maximum strictness level. So the way that we use TypeScript, not all JavaScript is valid TypeScript, but in other settings, that is the case. It's an NPM package, and that NPM package includes a compiler, so it compiles TypeScript into JavaScript, and you can target whatever level of browser compatibility you want. So with TypeScript, you don't actually need to use Babel at all. It's also a language server that provides IDE-like capabilities for a broad set of text editors. So instead of Vim and Emacs and Atom and VS Code each needing to implement their own IDE-like features for TypeScript, all of those editors can get autocomplete and type checking within the editor by using the capabilities built right into the NPM package. And it's an open source project from Microsoft, so thanks to all the people that are behind it. But today we're going to focus just on what I find to be the most interesting, exciting part of TypeScript, the type system. It's really the thing that when I took a look at it, I realized, wow, there's a lot of really cool stuff here. So that's what we're focusing on today. Really, everything in this talk is about what happens before you execute a single line of your code. It's just about things that are happening in your text editor as you type, or within the compiler when it compiles your program. So let's move on. So a little bit about what is a static type system. It's a logic system that derives constraints from looking at code structures and reasons about them systematically to find inconsistencies. It's not a lot of other things, so it's not about memory layout or code optimization. A compiler can use information from the type system in order to generate more efficient code, but the type system itself doesn't necessarily imply that. It's not a runtime metadata facility. Just because the compiler knows something about your code doesn't mean it needs to make that programmatically available to you. And it's also not necessarily about data validation. And in particular, TypeScript doesn't do any of these things. It's a gradual type system that's really there to help find bugs in your JavaScript code. And the thing that got me really excited about TypeScript is that I wanted something that would allow me to take a type-first approach to doing software development, which I think is summed up nicely by this tweet. When people say, but most business logic bugs aren't type errors, I just want to show them how to make bugs into type errors. And this for me was kind of the key aha after coming from a decade of doing development in dynamically typed programming languages. If we can take the invariants and the constraints about our program that we have in our heads at the time that we're designing it and hoist them into the type system, we can take what might be a production issue at 2 in the morning and turn it into a red squiggly in our text editor. It can also be a great tool for reteaching our future selves about what we had in mind and how we were reasoning about the system at the time that we built it. And when you do this, a lot of really interesting things that you don't necessarily expect to be type errors can be caught as type errors. In one of our React applications, we've made the type system aware of all of the different translations that our application supports. And if we have a typo in a tag for a translation, it'll point that out to us. Or if we fail to provide all of the interpolation variables that translation expects, it'll also give us a red squiggly. It's statically impossible for us to have a translation error in this program. So we don't have to click through our application and leave the email address blank only to find out that our Spanish translation is missing the error message when you fail to provide an email address. Another example that really, for me, opened my eyes toward the value that a static type system can provide is the ability to hoist permissions into the type system. So if we create a type to represent the permission to do a dangerous activity, such as editing a blog post, we can make a value of that type an argument to a routine that is going to go and perform that dangerous activity. And then that way we can statically prove that all code paths that are going to be updating blog posts on the website have first been checked for permission according to the user. So today I want to focus on three main aspects of TypeScript's type system that let us do this sort of thing. One is a little bit of an overview of how it's a structural type system and not a nominal type system and what that means. The second is we'll take a look at how it thinks about types as sets and how that can help us model problems, model constraints into the type system. And we'll also take a look at how it gives us a language for deriving one type from another. So first and foremost, TypeScript is mostly just the JavaScript that you're used to day in and day out. If you're ever wondering what TypeScript's going to do at runtime, it is literally going to do exactly what the JavaScript equivalent in your source file says it's going to do. But we can also define types, and we can use this colon suffix syntax to associate a type with a variable. TypeScript also does type inference, so we don't necessarily need to do so, but we'll do so for the most part going forward. TypeScript has all of the same built-in types that you'd expect of a C-like language. We've got booleans and strings and numbers. We can add square brackets at the end of a type to denote an array. We can use a curly brace style object literal type syntax to denote an object type. In this case, objects with x and y that are both numbers. We can surround types with square brackets to denote tuple types, so in this case, pairs of booleans and strings. And we can also have types for functions, so if we want to take a function as an argument or return one, we can have static typing support with that. Now, we can also give names to these types, which is pretty obviously important. And there are a couple different ways to do so, but we'll be using this syntax, the type keyword. And one thing that's kind of interesting about this is that it looks a lot like assigning a constant. We're saying type point equals curly brace, x number, y number. And the thing is that this isn't just a syntactic peculiarity. This gets at a kind of important concept in how TypeScript's type system works, namely that the actual type is the stuff in the curly braces, and we're merely associating a name with that type using the type keyword. And this kind of falls out of the fact that TypeScript is a structural type system. So a lot of mainstream statically typed languages are nominally typed, which means that the identity of the type itself is really important. If you have two interfaces in Java that both have the same methods on them, you can't use those things interchangeably because they're different interfaces, even though they require the same things of values of those types. TypeScript doesn't care about that at all. It just cares about what constraints the type is implying about the values that are in that type. So I kind of think a good metaphor for this is a nominal type is like a secret club that you need to be invited into, but a structural type is like just a set of minimal requirements that everybody needs to meet, and as long as you meet those requirements, you can waltz right in. So one way to kind of think about this, and this for me is a useful metaphor for reasoning about the type system, is that it's kind of a language for describing a predicate that must be true of all values that are going to be used in that point in your code. So the type point requires an x and a y that are both number. We can kind of imagine this as being describing the set of all values that are objects that are not null, that have an x and a y property that are both numbers. Since we use TypeScript at the maximum strictness setting, null pointer exceptions are not something that are possible by default. We have to opt into that. This has some other implications as well. So if we have another type named point, and this could come from anywhere, it could be from a third-party library. It doesn't have to have anything to do with our original point type. Because of the fact that named point also requires there to be an x and a y that are both number, it has natural structural overlap with our original point type, and because TypeScript doesn't care about the identity of the types, it cares about the constraints that are implied, named point naturally is a subtype of our point type. Anywhere we have a named point, we can use it as a point. So the set of points includes things that just have an x and a y, but it also includes all of our named points and anything else that's compatible. These tests that the types imply about our values are the minimum types that are necessary to ensure compatibility. They don't say anything about having extra things along for the ride, especially with object types. Other interesting things pop out of this as well. So if we have another type called named, that are things that have a type name, then we also see that named point naturally is a subtype of both of those things. It's kind of the intersection of both of these two types. All named points can be used anywhere a name is expected. They can also be used anywhere that a point is expected. And this is kind of, for me, something that was really great about TypeScript coming from dynamic languages. One of the things I like about dynamic languages is that if I write a function, any value that's compatible with the code within that function can be passed to it. In TypeScript, we can just make those requirements explicit, and it'll let us pass in any value that it can prove is compatible. And this makes structural typing feel really light. It's a really kind of nice balance of the flexibility that we're used to in a dynamically typed language with the safety and tooling support that we can get from a statically typed language. And this is great, but it's not what we need to really be able to model the invariants about our domain into the type system itself. We need more powerful ways of doing things with the type system. So let's take a look at a motivating example from F#. There's a feature called Sum Types, and this is built into a lot of different statically typed functional programming languages. Let's say we want to write a program that deals with shapes, and there are a finite number of shapes that we want to be able to support. So we might define our shape type to be either a square that has a size that's an integer or a rectangle with a width and a height. We can then define algorithms on that type. For example, a routine to calculate the area that can check which of the type of shape we're dealing with and then calculate the area accordingly. Now, there's actually not a lot that can go wrong with this definition of shape. It's statically typed. We can't pass a non-shape to a function that requires a shape. This pattern matching syntax, the match keyword, forces us to kind of prove which type of shape we're dealing with before we can use its subproperties. So we can't access the size of a rectangle or the width and height of a square because those aren't valid for those particular variations within the shape type. It also knows that there are exactly two types of shape, and it's proving for us that our area function is dealing with all of them. If we add circle to our shape type down the road, then F# will point out to us that our area function is no longer returning values for all of the different options. So let's take a look at how this maps into TypeScript. Well, it doesn't. Some types aren't a feature of TypeScript, but there are a number of different features of the type system that we can mix and match in powerful ways to get something that's pretty close to what F# can do for us. In particular, we have some type level operations that let us combine individual types into larger compound types. There's a feature of the language called control flow-based type analysis, where TypeScript understands the implications about control flow constructs, like if statements and switch statements, about the types that they're dealing with, and literal types, which let us go more granular than the built-in Boolean and string and number types that we're used to, and deal with things in a more granular way. So if we take another look back at our two types, point and named, our name point type happened to fall at the intersection of those things because we defined it just so that it would lie there. But if we wanted to construct a type that was guaranteed to always be the intersection of those two types, that might be a useful operation. And we can do that in TypeScript using the ampersand operator, which intersects two types. And so we could alternatively define our name point type by intersecting the types point and named. And if we do so, we already get some nice properties from this. If we change the definition of point or change the definition of named, those changes will flow through our named point type, and TypeScript will point out to us all the places in our code where our named point type is not compatible. So this kind of has its own imaginary predicate function constraining the values that type can take on. For some x to be a name point, it has to satisfy the requirements of both the point type and the name type. And for me, this is a useful mnemonic for thinking about why intersection is the ampersand, because it's kind of anding together all of the requirements of both types. And so with this, we can access x and name on our name point the same way we could before, but other things won't be valid. Now you might ask yourself, well, if we can intersect types together, could we also union types together? And sure enough, we can do that as well. With the pipe operator, we can construct a type that's allowed to be any value that's of one type or another type. So if we union together the number and string types, both one and foo are valid values of that type. Booleans are not. And TypeScript kind of has an internal understanding that whatever we're going to use there has to be either a number or a string. That's how I like to think about it, at least. So you might ask yourself, well, okay, why would I want to OR types together? And the reason is because it meshes really well with this control flow-based type analysis that TypeScript does. So this is about understanding what your if statements are proving about the types that they're dealing with. So if we have a constant that's of type number union with string, TypeScript won't let us multiply that constant by 2 because it could be a string, and we can't multiply strings by 2. But it could be a number, and sure enough, it's valid to multiply numbers. In order to do so, though, we first need to prove to TypeScript that we're dealing with a number and not a string. And we can do this using the standard built-in JavaScript control flow constructs that we use every day. So if we use the type of operator to prove that x is a number, control flow-based type analysis will cast the constant into the type number, eliminating the possibility of being a string within the then clause of that if statement. And in the else clause of that if statement, it will eliminate the number possibility because we've disproven it, and it'll let us treat that constant as a string. So if we want to define a function double that's going to take a number or string and double it, then within this, if we were to hover over the x in the if statement, at that point it's a number or a string, but when we go to return 2 times x, TypeScript understands that it can only be a number in that case. And similarly in the else clause, it knows that x is a string, and so we have to treat it accordingly. So we can start to see that there's some overlap between these two features and the capabilities of the sum types that we saw in F#. So let's take a look at how close we can get to this with what we've seen so far. We could define a type square that has a size that's a number, or a rectangle that has a width and a height, and then we can union those two types together. One thing that's kind of interesting about this is that the types square and rectangle are just standalone independent types that we can use however we want, and we can assemble those together with a union operator to construct a larger compound type that could be either of those things. And we can define our area function, but we start to run into some problems here because we don't actually have a good way of distinguishing between whether or not we have a square or a rectangle. We can do so by using the built-in in operator to test whether or not size is a property, but it's kind of not very savory to prove that we have a square by testing for some property that square happens to have. So let's see, can we do better? And if we look at the example from F#, we have this kind of nice declarative way of saying, if we're dealing with a square, let us treat it as such, and if we're dealing with a rectangle, let us do so accordingly. So the solution to this in TypeScript is to take a closer look at those built-in types that we saw at the beginning, Boolean, string, and number. These types are sets of values. Booleans can be true or false, strings can be foo or bar. And in a lot of C-like languages, the most granular you can get is Boolean or string or a number. We can define a variable or a parameter to be a Boolean, but we have no control over whether it's true or false. We can define something to be a string, but we have no control over which string, statically at least, which string that can take on. But in TypeScript, every literal data structure can also be used as a type. And when we do so, it denotes a type containing just that one runtime value. So if we wanted to, we could union together the types true and false to denote a new type, myBoolean, that could either be true or false. And because of the structural compatibility properties of TypeScript, this is directly equivalent to the built-in Boolean type, and we can use the two interchangeably. Or we could union together the types literal string OK with literal string error, denoting a type that could be one of those two strings, but no other string would be allowed in that case. And this doesn't just apply to the atomic types, but we can also apply it to compound types. So if we wanted our result to not be a string, but to be an object, we can union together objects that have a status OK and objects with a status error. Now, this does not denote exactly two possible values for a result because the compatibility constraints imply that we only care about status. So our result could have additional fields, but if we're treating it as a result in this case, we won't be able to access those. But if we wanted to do so, we're not actually limited to just literal data types here. We can use any type that we want. So if we wanted to denote, to have just one successful case, but have an infinite family of all the things that could possibly go wrong, we could add a reason property that's a string. And then now we are always guaranteed that our failure case will have a status of error, but the reason can be any description that's appropriate. And this is actually the solution to doing sum types in TypeScript, often called discriminated unions, is to add a property common to all of the types that we're unioning together, but to use literal types to denote very specific values that the type system can understand and use for us. So we'll add a kind property to square that's guaranteed to be the string square, and a kind property to rectangle that can only be the string rectangle. And then with this, we're actually about as close as we can get in JavaScript or in TypeScript to the sum types that we saw in F#. So given a shape S, if we switch on the kind of S and prove that it's the string square, then TypeScript will automatically convert S to a square for us within that case clause and do the multiplication. Within the rectangle case, we can multiply the width and the height. And this actually has a lot of the safety guarantees that are in the F# example, if not the syntactic elegance. we know that we're getting a shape, so TypeScript will ensure for us that anything passed to it is compatible with the shape definition. We won't be able to access the size of a rectangle or the width and the height of a square because those properties aren't present. And also, TypeScript will prove for us, it'll do exhaustiveness checking. So if we add circle to our shape type down the road, then this definition is no longer guaranteed to return a number. And so TypeScript will point out to us that we're missing a case, and we can come back and add it to deal with our circle shape. And this, for me, is the kind of cool and exciting part of TypeScript, is that there's a lot of little capabilities within the type system that we can combine in powerful ways to model the constraints and invariants that we know to be true about our business domain or our abstractions and bring them into the type system. So this is great. Actually, sum types are kind of bread and butter way of making invalid states unrepresentable in our applications. We use them all the time. A lot of what we do is based on unioning and intersecting types together, but sometimes we need to be able to express more complex relationships between types. And the way that we can do that in TypeScript is using generics, using a similar similar syntax to what you'd see in C# or Java. So we can add angle brackets to a type definition to denote a generic type, which you can kind of think of as a function that takes types as inputs and produces types as outputs. So if we wanted to create a stack data structure of some underlying type T, we could then instantiate that for some type that we have. If we wanted to have a stack of animals lying around, then we could do so. And if we grab the top thing off of our stack data structure, TypeScript will have preserved for us which type of stack we're dealing with, and let us use that variable accordingly. And this is something we can do in any language with generics. We can take some opaque type T that we don't really know anything about and wrap it up in some structure. And this is why generics are used for collections in pretty much every language. But what if we want to do something a little bit more sophisticated than what's built into than merely accreting structure around an existing type? What if, for example, we want to be able to take some arbitrary object type as an input and then produce a new type that has the same structure except every single property has been made optional using this question mark syntax in TypeScript? So one reason we might want to do this is to have a generic update function that takes some object as an argument and a subset of its properties that we wish to update and give us back a new instance of that type with those properties updated. I'd like to be able to do so without accidentally updating the title of a user or a first name of a blog post. And in order to do that, we need to communicate to the type system that there's a relationship between the type of the first argument to update and the type of the second argument. Namely, whatever we pass in for the first argument, we want some subset of those properties used in the second argument. So what we need is a little function, a little program that can pull apart the type that we're using for the first argument and build back up a new type where every part of it has been made optional. So we need ways of actually manipulating types the way that we manipulate data. In a lot of statically typed functional languages, there's a phrase for this, type-level programming. We can kind of think of there being two different levels of programming to a statically typed language with a powerful type system. One is the value level, which is what we're used to. It's data flowing through our system, variables, that sort of a thing. But we can also think of programming in terms of types as well to allow us to do these sort of derivations of types from other types to communicate more powerful invariants about our domain. So let's take a look at how we can do some type-level programming in TypeScript and how that maps to the concepts that we're used to on a regular basis. So we've already seen the analog to constants in TypeScript. We can use the type keyword to associate a name with a type the same way we can use the const keyword to associate a name with a value. Now, because TypeScript is structural and it doesn't care about the identity of types, it only cares about the constraints that those types imply, we can actually substitute anywhere we see the name of a type, we can actually substitute it for the underlying structure of that type. Those two definitions of P1 are effectively equivalent. There's some differences in how error messages get reported, but they constrain the values of your program in the realm of value types in the same way. And this notion of substitutability is really important. It's kind of a foundational principle of how to reason about functional programs, pure functional programs. And we can actually think about how the type system executes and evaluates our generic types in TypeScript the same way that we think about how a functional program executes by repeated substitution of lambdas. So Let's look at a simple example of that. If we take another look at our name point type, we see that we have a name. We have our name type and our point type. We can substitute those names for the underlying type definitions. And so we have objects of type that have a name that's a string intersected with objects that have an x and a y that are a number. Now, the intersection operator is built right into TypeScript, but it has the effect of kind of unioning together all of the properties of those object types to produce for us our original definition of name point that had a name that's a string, an x and a y that are both a number. And so we can kind of see, we can reason about how TypeScript will repeatedly expand these types to produce an output structure for us. And this is kind of a general way we can think about what it's doing with our types within the type system. And this is all, none of this is running at runtime. This is entirely running within your type checker within the compiler. Generics also map in a really direct way to functions, so we could create an identity function that takes a value x and returns it. We could create an identity type that takes a type t and returns it. We could create a function that takes an x and a y and returns a pair of x and y. We could create a type pair that takes types t and u and returns the tuple type of those two things. So a lot of the things that we're used to thinking about in terms of functional programming in the value realm map into the type system as well. So we start to see that there is a way we can reason about solving this sort of problem. Now, partial is actually built right into TypeScript. It's in the standard library, but it's just using more fundamental things that are built into the type system. And so we can actually take a close look at how this actually would execute. So if we take a look at the problem at a high level, we can kind of see that this has a similar shape to something we do every day. Namely, we need to map over the properties of our object types to produce new corresponding properties in a resulting type. And so the way that we can do this in TypeScript is with this type definition, which I'll unpack in a minute. So partial is a generic type that takes some input type t and then uses this syntax to expand to the result type that we want. So let's kind of substitute through this and see how it executes. So let's start by replacing t with the type point that we want to deal with. Now, this is directly equivalent to the curly brace syntax we saw a moment ago, but it just gets a little messy. So you can imagine curly brace xy number here if you wanted to, but we'll just stick with point. Now, if we look at this at a high level, we can kind of see that syntactically this looks like a lot like list comprehensions in Python, except this is more like an object type comprehension. We're saying for each k that's a key of our type point, then let's produce a property in the output type that's made optional by the question mark at the end of the first line, and whose corresponding type is computed on the second line by subscripting point with k. So there are three things going on here that are being combined together into a little function to produce the resulting type. Key of point is built in. It takes an object type and returns a list of all of the known properties of that type. The overall syntax is called a mapped type, and TypeScript will just iterate through whatever individual entries are in the list returned by key of and produce the corresponding property in the object type for us. And then this subscript syntax, point subscript k, works the same way in the type system that it does in regular JavaScript. So namely, in the value level, we can subscript an object with a string to get the value associated with that string in the object. We can subscript an object type in the type system with the literal string type to get the corresponding type of that property in the object type. So we'll start by substituting key of point with its result, which is the string literal x union with the string literal y. So union types within the type system also serve double duty as sort of a list. Now, the overall comprehension syntax understands that, and so it will iterate through that list and let k take on each individual entry within that union. Expanding for us into an object type that has x that's optional and y that's optional, and where the individual values of k have been substituted into our point subscript. Now, because point has the type number for the x property, and it also has the type number for the y property, those substitute out to be the number type, giving us the result that we were hoping for originally. So we've kind of seen that there's a built-in idea of mapping over object properties to produce a corresponding object type. There's a key of operator to give us the list of properties built into an object type. We can use the subscript syntax to get a type corresponding to a specific property of an object. All things that we need to be able to manipulate in more sophisticated ways are object types to do more sophisticated derivations of new types. A couple of things worth noting. we're used to using if statements all the time in our value level code. There's actually a direct correspondence in TypeScript type system. In the type system, within the type checker in your text editor, you can actually test one type for compatibility with another type and then make decisions about what to do based off of that. And we've also already seen that recursion is built in, and we can do mutual recursion and that sort of a thing. And this for me was like, when I started to see this in TypeScript, I was like, wow, there is a built-in functional language built right into the type system. And it's a type system for JavaScript, one of the wartiest and most practical languages on the planet. So a lot of this stuff isn't stuff that we use every day when we're developing in TypeScript. It is a very powerful language. I don't think it's quite Turing complete, I'm not sure, but everything's based on substructural recursion, so as far as I know, everything always terminates. I've certainly never kicked the type system into an infinite loop. But this isn't the normal thing that we're doing day in and day out. For me, this is really more of a sign that there's a lot of depth within the type system that can really reward mastery. The time that I've spent learning about some of the more advanced or niche features in TypeScript's type system have really paid off in my ability to do powerful things, rule out bugs that otherwise pop up at runtime, make translation systems that statically rule out references to rules that are incorrect. And this for me was a really interesting, fun exercise, seeing this marriage of one of the most practical languages on the planet, JavaScript, with this cool, powerful, elegant type system that at least, if nothing else, papers over a lot of the warts that are built into that. And it's led to a better development experience, higher quality products, better outcomes for our customers, and I've really enjoyed it. So there we go. Thank you very much. I think I've got some time for questions. So the first question is, does structural typing eliminate certain forms of hoisting business logic into the type system? So with a nominally typed system, one thing that's nice about it is it does deny implicit conversion between types that you don't want to be implicitly converted. So with a structural type system, that doesn't happen by default, but there are tricks that we can do to kind of convert a type into a sort of ad hoc nominal type. So one of the things that we'll do is we'll add virtual properties to a type that force an inconsistency with other similar types, and that way we can have the nominal typing property in the places where we want it, but without having the lack of flexibility that normally comes with it. One way that we use this is to support units, so we can introduce type incompatibilities between different forms of numbers by associating with them some virtual properties in the type system, so that it disallows mixing, for example, inches and gallons. So let's see. What are your least favorite parts of TypeScript? What are the agreed upon weaknesses of the language? My least favorite parts of TypeScript are all JavaScript. Because TypeScript is based on the JavaScript ecosystem, we're mostly using third-party NPM packages, and those, by and large, don't have well-formulated types associated with them. So there's a big open source project to create types for a lot of popular open source JavaScript libraries, but in a lot of cases, those types don't actually correctly capture the semantics of the JavaScript library itself. So there can be a fair amount of pain in using third-party JavaScript libraries and having good TypeScript support for those, which can be a little bit frustrating. But at the same time, it's usually one of the things, because TypeScript is a gradual type system, you don't actually have to use strong, like static typing, really granular static typing everywhere. You can actually just say, this part of the code treat as JavaScript, and don't try to check anything about it. So what we'll often do in those cases is we'll wrap a pure JavaScript library or a poorly typed JavaScript library with an API where we provide types ourselves, and we have a little bit of untyped code within a well-defined statically typed interface, and that helps alleviate the issue. Do folks use TypeScript to implement monads? So there isn't, TypeScript has this really kind of strict rule. They don't introduce any runtime code that you didn't write yourself. And monads aren't a feature of JavaScript, so they're also not a feature of TypeScript. I think you can get part of the way there. I mean, there's async await and promises, which I think are a monad. I don't know if you can do some clever hacks to do something with that. And I've also seen people use kind of fluent object syntax where you repeatedly chain method calls on an object with lambdas to kind of get somewhere in the vicinity. But no, that's not built in. And there are definitely some cases where we're using like an either result type where we really wish we had a monadic syntax. But I haven't seen that myself. I haven't also really looked at it. How do you test types? Ooh, I love this question. This is great. So we found an NPM package called typing's tester or typing's checker, where you can create a TypeScript file where you create a bunch of individual expressions where you define, say, a constant of some type and assign a variable to it. And some of those should type check and others should not. So there's a magic comment you can add in those files to say expect a type error on the next line. So what we can actually do is we can use that to test drive our type first development process before we test drive our value level process. So that ends up being pretty useful. You can kind of just say, here are a bunch of examples of things that should type check, here are a bunch of examples of things that should not type check, formulate the types for those, get that test to pass. Now you have a type definition that very, very accurately encodes exactly what you want to be able to do with the value level, and then you have the help of that in both writing your value level unit tests and your value level code. So how would TypeScript handle intersecting types with members named the same but different fundamental types? I believe what happens there is they give the example of having two objects that both have an ID, one of which is a number and one of which is a string. I think that in the resulting type, I'm not sure about this, but I think in the resulting type, the ID property would be something that's both a number and a string, which is an impossible type. So it would intersect those together for you, but you'd have a really hard time providing a value that, that meets that requirement. All right. How does TypeScript handle function composition and higher order functions? It handles those quite well. So I didn't really get into it, but you can define generic functions. That's really probably one of the most common ways we do some of the things that I showed here today. And with that, you can create generic higher order functions, and it works quite well, similar to a lot of other statically typed functional languages. And I think that'll be it. Thank you very much.